We don't have enough bandwidth now to handle the demand. What are we going to do with big data and even more video? I wish there was someone I could ask about that. Well, hey, John. How are you doing?
Hey, Clinton, good morning.
Good to see you.
Good to see you.
Yeah. So I've been trying to watch this video on my phone, but it's just taking forever.
Yep.
And so this is the problem with the internet now. And demand is just increasing with big data and more video. How are we ever going to meet that demand?
Well, it's funny you ask, because that's really one of the problems that we focus on here. Well over 3 billion people have access to the internet, and every single one of them and you and me and everybody else want more information, more data, more video, social media, all that stuff.
We've got to watch our cats.
That's right. And so you begin to think about it, and all that data goes through a small glass optical fiber the size of your hair, and you know, there's only so much we can pack on it.
So the optical science and engineering, that's, you guys are building the internet highway. You're building the pipeline.
We are.
So what are you gonna do about that?
What we focus on here is understanding the role that the glass itself, that the fiber is made out of, how that glass interacts with the light that's going through it, and how all of those things come together to influence the amount of light that we can get out the other end. Out of this lab in Anderson, South Carolina, we have an industry-grade capability to make some of the world's most advanced optical fibers and then test them, either here or with some of our partners around the world.
Yeah, so maybe you could show us some of that stuff?
Sure could.
Cool, let's go check it out.
All right.
This is where you make the magic happen, huh?
Sure is.
What do you call this place?
This particular lab is a chemical vapor deposition unit, or vapor deposition process that is used the world over to actually make the glass rods that are then ultimately drawn into fiber.
So what's actually going on here?
So you have a lathe that functions just like, you know, a woodworking lathe or a metalworking lathe. But the difference here is that we have a tube of very, very, very pure glass. And then inside of that tube, we flow a variety of different gases.
Okay.
And those gases react at high temperature, and they form a powder of glass on the inside wall of that tube.
Gotcha.
And then we just layer by layer by layer by layer, we just create this glass from the outside in. And then ultimately that tube gets collapsed down into a solid rod that has, from the outside in, a variety of different glass compositions. And it's from those compositions that we tell the light how to behave. The outside is the original tube, and then the inside, which is where the light ultimately goes, is the layer by layer by layer that we developed from these gases. This then, we hold on to it, and all the way up at the top, it gets lowered into a furnace, which is that cylindrical unit that you see. And you see a big piece of glass going in the top, and you see a small little hair-thin fiber coming out the bottom.
Wow. And
that's, again, just glass. Looks like fishing line. We have collaborators all over the world. For the projects that we're talking about with issues associated with scaling of lasers to higher power from the military, or some of these other aspects of communications, our go-to is a professor named Pete Dragic at the University of Illinois. Hey Pete, here's your fiber.
Thanks, John and Clinton. Absolutely, improving the quality of the fiber can increase the amount of power that we can propagate through it or generate in it. We can also enhance the power coming out of fiber lasers, which certainly can enhance, as you mentioned, military systems, but also civilian systems such as LiDAR. What's cool, no pun intended, is that you can actually tailor the spectroscopy of the glass with its composition, and that can favor an application that we call laser cooling. Oh, another thing that we do with your fibers in this lab is actually to build lasers out of them. The active fibers themselves are certainly designed for the laser application. They possess these elements, the rare earth elements that are found at the bottom of the periodic table, such as thulium or erbium or ytterbium, and you can make lasers out of those. So John and Clinton, that kind of summarizes some of the measurements that we make on your fibers. Your ability to compositionally tune them to suppress nonlinear effects will most definitely enable the lightwave systems of the future.
Thanks, Pete, for showing us what you do there at Illinois with the fiber that John and his folks make here at Clemson. I'm going to go upload a video of this as soon as I have enough, bandwidth to do it quickly. So
Good to
thanks
see
a
you.
lot, John.
My pleasure.
Good to see you.
Thanks, you too.